Hello, everyone. Welcome to my session at NDC, Sydney. Good afternoon to audience from Australia, and good day from if you are watching it from elsewhere around the world. Today, I'm going to talk about how we can build enterprise microservices using Ocelot and Azure. Apparently, the Ocelot here has got a set of Azure eyes. My name is Patrick Zhao. I'm currently working as a senior software architect at SSW Melbourne office. I'm a full stack engineer and speaker. Here's my Twitter handle. If you want to be a little bit more formal, there's the link to my LinkedIn. And at SSW, each consultant has his own profile page. You can easily find me by Googling Patrick at SSW. In my spare time, I like to follow some great open source projects over GitHub and also contribute to some of them. My recent interest being a conversational AI chatbot that can serve as a virtual receptionist. So if an organization wants to set up a virtual receptionist that can help its guests to find its employees with certain skill sets and availability, you can feel free to download and spin it up in your own environment. Come have a look. I also have a personal blog. I see it's a great place for me to every now and then retrospectively summarize the lessons I've learned from my recent projects, my understanding for some new technology. So since I graduated from Melbourne Uni, I have been in the IT industry for over 7 years, during which I have successfully led, architected, and delivered a great number of solutions for my clients across different industry, with a special focus in fintech industry. And my expertise and interest includes big data, machine learning, AI, and most importantly, Azure. I've been recently helping a client to migrate a joint application from a classic but a bit old school monolith architecture to modern microservice architecture. And that's why today I'm happy to share some of the knowledge and lessons and challenge that I learned and or got from that project. So here's today's agenda. First of all, when we talk about monolith, does it mean it's bad or it's a mess? Or when we talk about microservice, although it's more modern and more up-to-date, does it mean that it's perfect? Let's do some comparison so that we have some overview, overarching understanding of monolith versus microservice. Then I'll spend some more time to have a deep dive into the microservices and with a focus on what kind of pattern that we should advocate when we are trying to implement microservice and what are the key elements a microservice solution is composed of. And then we'll narrow down and be more specific to Azure, what type of services we can leverage to build our microservice architecture. And as the way that I usually delivered a presentation, I prepared a demo, which is a quick POC of a simplified version of a microservice architecture that we can use, that we can build on Azure. Okay, so monolith. So what is a monolith? Doesn't mean that we have a bunch of Lego bricks which are completely unorganized and a mess. No, it's not. Monolith is a unified architecture where I see it as a very clean and clear architecture. So what it means is that you have your user interface that the user interact with, and all the way down, it follows a transaction script pattern that the upper layer, for instance here, the user interface interacts with the downstream layer, the business logic, and business logic interact with your data access layer, and data access layer runs CRUD operations with the data store, and it returns the data all the way up. So the monolith architecture is actually quite clean. So it's not a bad thing. It's not evil to use monolith architecture, but it has its own problem. So next, let's look at what are the pros and cons a monolith architecture has. So the biggest advantage when we use monolith architecture is that it's self-contained. It can have a lot of features, functionalities within the box. But once it's done, it's self-contained. Once we've done the DevOps, once we've done the pipeline to release it, once we've configured the hosting environment, it's done. It's all self-contained. So we only need to look after one suite of environments or artifacts. So that way, we can narrow down our eyesight to look after a particular thing, although it can be very complex inside. And since it's self-contained, so it's easier to test and debug. And mind you, here, by testing and debugging, I mean treat the monolith application as a black box. So this is more from the integration test perspective. If we don't need to break it down and dive very deep into the solution itself, but we rather throw some inputs to it and assert on the output, then it's easier to test. And there's less overhead in cross-module communication. Usually, so if we take .NET as the programming language, usually the cross-module communication is done via DLL. If you build your application in Node.js, it's the cross-module communication is done by referencing npm package. So there is no network traffic, no gRPC call, no REST, no Graph API call, nothing like that. So the overhead is minimal. With all that, although over time, when your business logic grows more complex, monolith architecture might have problem. But to begin with, if you are not sure about the potential scope that your application is going to grow in 3 years, say, it's easier for you to just start with a monolith architecture for your greenfield project. So we've looked at all the advantages. Now let's look at some disadvantages or the potential problems. So I put an asterisk on this first one, just to remind you that when we say that a monolith architecture can be easily coupled, but only if it's done wrong. So what I mean is that even with monolith architecture, if we follow clean architecture and we incorporate it with some good patterns such as CQRS, command query responsibility segregation, or event sourcing, I'll expand on those architecture later, because those architecture can also be used in microservices architecture. If we've incorporate these clean architecture and good cloud patterns into our monolith application, the monolith would become a modular monolith. So this cost can be flipped to pros if we've done it properly, but it's very hard because of some other issues that I'll show you shortly. The second one is it's hard to update individual feature. Again, this downside can be flipped to our upside if we've done it properly. We have a modular approach. Then each individual feature can be updated individually. But there's a hard block with the monolith application, being it has a massive code base in a single repository. What this means is that since our monolith is self-contained, so we have to have everything in your repository, including your database migration scripts, your application code, your most of your configurations. What this results in is that when a developer tries to pick up some product backlog item, they need to have at least a minimum understanding at a holistic level. So without an understanding of the overall application, you won't be able to even start working. The other hard roadblock is the scaling. The scaling is also holistic. You either have to scale the entire application because it's self-contained, deployed in one single hosting environment, but it will incur unnecessary cost. I'll also expand on that in a bit. So with all the downsides a monolith application has, some organizations are thinking about moving from monolith to microservice. And this happens when there's a giant legacy system, which could be smoothly running or getting some patches and some minor fixes over the last 2 decades. But when we are trying to migrate this type of application for whatever reason, maybe some technology is end of its general its GI supports, we need to migrate. Then when we try to migrate this big giant system, it's very difficult and risky to migrate them all in one go. So what we tend to do is what we call a strangler fig pattern, that we want to migrate the application bit by bit. And this way, there are less risks and it's easier to manage the overall project. We can cut it to smaller milestones. And the deliverable of each milestone are easier to manage and easier to scope. Secondly, we've mentioned that in the previous slide that the scalability for a monolith application could be a problem because you have to scale at a holistic level. So if only a certain part of the system needs to be scaled up and down, in or out, microservices is the way to go. And lastly, the microservices tend to increase your development team's productivity because by embracing microservice architecture, your engineers tend to only require smaller amount of knowledge from the business domain's perspective, because they only look after a certain part of the system. So they don't need to have a overarching understanding of the entire business, so they can spend more time in delivering. So here's a good analogy that I found on Google. So for instance, we have a Lego pyramid, and if something goes wrong, for instance, we want to replace this green brick. So if it's a monolith pyramid, what we have to do is that we have to put down at least the top 3 layers in order to replace this small brick. Whereas if via some reconstruction, once we've migrated to a monolith, a microservices architecture, if we were trying to replace a small break, if it's been corrupted or whatever reason, we need to replace it. We only need to put down this small module and reassemble it once we've fixed this small break. So as we can see, the cost of managing a microservice like patching or bug fixes can be reduced if we've done microservices properly. So now we've had an overview of monolith versus microservice. Then let's move on to a more in-depth discussion of microservice. Let's start with the key components. First of all, usually we want to have an API gateway that serves as a single point of entry. And that API gateway can sit in front of your subsequent microservices and serve as either a proxy or handle more complex scenarios. And we want to support different types of front end. It could be web, desktop, mobile. And we also want to be able to deploy our subsequent services in a flexible way. And each microservice needs to have its own data store. Here, the keyword is data store rather than database. So multiple microservices can potentially share the same database, but if they share the same database, they need to own its own schema. What it means is that we should prevent cross-service data access. And this is the key principle and the pattern that we should follow when we are building microservice. And we want, so from the coding pattern perspective, we want to advocate the event-driven pattern. And personally, I like to integrate my microservice, especially whatever sitting behind the API gateway, to be protected by VNet. So that way we can have less worries about the security and compliance practices. And we want to leverage messaging system because each microservice has its own data store, but sometimes we want to interact with the other data store or external data. Then usually we need some messaging system. I'll explain all these components in details in a bit. So here's a great example that Microsoft has posted on their document repository. It's an e-commerce site, and they use this to illustrate the microservice architecture. And they've been actively updating it. For instance, in like a year or two ago, when I saw and referenced this example, they advocate Ocelot, but now they use the Envoy instead. So that means that as technology evolves, the Microsoft has been looking after their documents examples actively as well. So it's a great resource. So as we can see, we have an API gateway which has different variations. We have an API gateway that serves as a facade to your APIs, or we can have a backend for front end if you want to support different type of front end applications. In this example, the hosting environment, they host the applications as Docker containers, but there are other deployment options, which we'll touch on in a bit. The most important insight we can get on this example is that each microservice has its own data store. The data store can be a SQL database or can even be a Redis cache. If we want to interact between services, we do that via a messaging system. On Azure, we have Azure Service Bus, or you can host your RabbitMQ on it. Okay, so let's move on. So I just mentioned that there are different deployment options rather than Docker. So let's have a look. So first of all, we can leverage PaaS services on public cloud providers. On Azure, there are a lot of options. Or we can choose to have containerized applications. On Azure, there's Azure Container Instances. And recently, Azure has rolled out Azure Container Apps, which I personally didn't have much knowledge about because it's new, but I like to explore because they advertise it as a serverless containerized environment, and it has a smooth integration with Dapper, Dynamic Application Runtime, and Kida. So it's great. I like to explore on that as well. Or we can always use Kubernetes if we want to manage the cluster ourselves, and we have the expertise and experience in managing that. On Azure, there's AKS, and it's a great deployment option. So we've looked enough on the technical side and on the development team's perspective. If we start embracing microservice architecture, it's not just about a software or solution architecture, but also about a methodology and also a development team management. So we can onboard our new developer in a fast pace and more effectively. And because we can onboard the developers quickly, so developers become pluggable. You can join a microservice team and do some work and finish off and join another team if there's need. So we can adapt to business requirement change quickly as well. So there's a nice chart here. So a monolith application, because it's so simple to start with, so the development speed could be very quick at the beginning, but as time goes on, over time, the productivity is going to drop. Whereas in comparison, the microservices, to begin with, you have a lot of cross-cutting concerns to worry about, and you have a lot of things to set up. So at the beginning, when you're setting up the foundation, it could be slow, but over time, the productivity is going to grow because you don't need to have a overarching understanding of everything of the entire solution, but you can rather just focus on a small piece. Okay, so from development to release, we have a DevOps exercise. In advocating microservice, we can adopt the real agile. We can adapt to the changes and have a faster iteration. And the most important thing I like to highlight is that compared to the traditional monolith application, the concepts of deployment and release should be separated. So what that means is that we want to have a progressive release strategy in which we can use dark launch, or we can toggle features on and off. So what that means is that, for instance, we have a feature and that's handled by a single microservice. It's easier for us to turn it on and off. So we can release these features to the markets without a formal notification to the users. So we can collect some user telemetry and get the feedback to improve our application. This can be done with Monolith if we do Monolith properly, but with microservices it is much easier. So we've looked at all the goods and benefits and all the upside of microservices. Let's look at some potential challenges and the traps. The biggest challenge is that in microservice architecture, we can potentially get into a circumstance, get into a place that we call micro monoliths. What this means is that, sure, if we've done microservice properly, we don't have cross-service reference. Each service has its own data store that will all follow event-driven pattern. But for instance, there is a method that's sitting in a module that need to be referenced by 5 different services. And if we make some change on that module, all the 5 different services need to would be impacted, which means that we have to run tests. We run a lot of tests to make sure that our change on that service doesn't break in that module doesn't break those 5 services. If we have a lot of modules like that, we get into a situation that although our services does not reference each other, but they all reference the same thing. So this is a micro monolith. We should avoid that. And the way to avoid that is that to try to package your module and publish them as programming packages. So in .NET, we have NuGet. In Node.js, there's npm package. And by properly packaging them and shipping them to the NuGet, we can have a proper versioning. So the services can choose to upgrade if they want to reference some updates in the package, or the other services can stay with the older version of the package if they don't want to change. So this way we can make sure the impact is minimal if we make change in the shared library. The other thing is from the data perspective. We don't want cross service data referencing, but sometimes we have to. For instance, we want to in a typical e-commerce application, when we are checking out, we want to reference a customer's information such as their address with the transactions, with the payments that settled and the transactions that posted. So that way, the payments service or the order service need to reference the customer service. And there are 2 ways we can achieve it. The first one is to reference external service. What this means is that your checkout service can emit an event or can call your customer service directly. But regardless of which way, by following this approach, we create a hard dependency between the primary service and the dependent service. And if your external service goes down, you need to work out a way to mitigate the problem. And what we do, we either retry or we've been held up. As an alternative solution, we can duplicate some of the data in the microservices data store. So as we know, storage is very cheap these days. So duplicating the data would incur an additional storage. It's not a big issue. However, because we're duplicating data, we need to be careful about the consistency level of the data. For instance, if our customer service is going to provide the referencing data for a user, and we need to synchronize that data across to your checkout service. Then we need to guarantee that when the user is actually checking out, we get the latest and the latest address, the home address of the customer that we're checking out. So the data synchronization process need to bear in mind the data it synchronizes need to have a good consistency level that's acceptable by the primary service. Of course, eventually the data is going to come through, but the data might be stale at that time. So there's consideration that we need to take into account. And that can, at a higher level, can be summarized as a reliability for individual services, because there could be potentially be dependencies between the different services. If we are not doing it correctly, there could be some issue that when a service goes down, it affects other parts of the system. And the last one is the most difficult one that I personally don't even have a good solution for it, is the domain boundary. So what that means is that when we are cutting different piece of your business into different problem domains, so that each problem domain by design should have a microservice to look after. If we are not setting the boundary between the problem domains properly, what it would potentially end up is that we can have some microservice that act as a monolith, which handles a lot, while some other services handles a little. This is something we should avoid. And from my understanding, the real way to there's no quick way to tackle this, but it all depends on your knowledge and experience with the business domain. So next, let's look at individual parts of a microservice architecture. First of all is the API gateway. It's a single entry point, and API gateway is nothing but a bunch of middlewares, so that the cross-cutting concern of let's take HTTP request as an example. The cross-cutting concern of an HTTP pipeline can be abstracted out, put to its own layer that sit in front of your microservices. So microservices can be doing its own thing rather than worrying about your cookie affinity, your JWT token validation, so on and so forth. So there are several tasks an API gateway should perform. The first one is the simplest scenario where a API gateway is just a proxy. It proxies the upstream incoming traffic and route them to the subsequent service. Sometimes it's more complex that you need to fan out. When the API gateway emits routes some message, multiple services need to react. And thirdly, there's an even more complex scenario where the API gateway need to orchestrate or aggregate. When the front end asks for the data that's spread across multiple services, your API gateway need to fetch data and orchestrate them before it gives response to front end. And as we showed on the Microsoft example, there's a backend for front end requirement for some of the API gateways. So let's look at Ocelot. So Ocelot is a great library that can help us to build a API gateway quickly. It's a bunch of middlewares that's being executed in a specific order. So you can see that Ocelot as a big middleware in your entire solution at solution level rather than your .NET Web API or MVC level. And Ocelot started to support WebSocket, which it didn't used to support. So it's great. So there are other options for API gateway apart from Ocelot. Ocelot is not the only choice. For instance, there's Envoy. So Microsoft's example started to use Envoy. So it's a great alternative. And there are past offerings on cloud providers. Let's take Azure as an example. We can use API management or application gateway. They are different, but I'm not going to spend too much time in comparing these options. There's just one thing I like to highlight is that when your API gateway grows to a certain complexity, or you want to monetize it, at that moment, you should start thinking about using a PaaS service rather than manage it yourself. And of course, we can build up API gateway in your Kubernetes cluster. For instance, we can leverage Nginx as your ingress controller. And I like to integrate my microservice architecture with VNet so that we can use it to protect the subsequent microservices, while we only need to expose the API gateway to the public. So this way we can ensure that the traffic between the microservices are on the backbone network that's offered by the cloud provider or Azure, for instance, instead of going via the public internet. So this way the compliances and security can be guaranteed. Next, let's talk about cross-service communication. The first pattern I like to highlight is the Saga pattern. It has two variations. The first one is the choreography. What this means is that, let's take e-commerce as an example. You might have an order service. Then when a certain event happens, for instance, your order has been created, the order service is going to emit some event, and some other service, in this case, your customer service may need to react to the event that's emitted by the other Saga. And once it's sorted out its own business logic and change the state of a transaction, for instance, from the credits reserved to credits exceeded, or credit limit exceeded, or the payment sorted, whatever event. Once it's done its own operation, it's going to emit another event, so other Sagas can react on it. So this way, the events are trained up, and they're being flying through different microservices smoothly. There's an alternative to this choreography pattern that is called orchestration pattern, that you have a single place that acts as an orchestrator, that when the events need to be emitted, it sends through a message broker. And when the other Saga reacts on it, you get the message back, and then you fire off another event from your orchestrator. So either of these pattern works, but they are all event-driven pattern, which is good for microservices architecture. So as I mentioned, we want to have event sourcing when the state of something changed. So within the Saga pattern, when a particular transaction state has been changed, we want to be able to trace the state change. And sometimes if we want to rewind or replay, so the event sourcing pattern is a great choice for that requirement. And by in implementing all the Saga pattern or event source pattern, we need some PubSub messaging service. And at last, I like to mention caching, but I also want to remind everyone that we need to be careful with caching. So, for instance, if your external dependent service is going down, then you need to have some type of caching to make sure that you still can get the data. But you need to be careful that you don't get the stale data. So we need to introduce something called a circuit breaker pattern. Not the real circuit breaker, but it works in a similar way that whenever there's some abnormal currents going through your circuit, we need to open it. So whenever there's some abnormal events like the external service goes down, you want to make sure that the service does not constantly ping and constantly get an error, but it will stop pinging it. And when the external service goes back, we want to re-establish the connection, but only allow a certain attempts of retries. And we want to make sure that the states are remembered properly. So there need to be a state machine to handle that. So we need to be careful when we want to use caching. And so we've gone through the elements and the pattern that we can use to build microservice. Let's see what are the services available on Azure can help us. First of all is VNet on Azure, and Key Vault. We can store our secrets and credentials on Key Vault that multiple services can all reference using managed identity. So that's why we don't need to store the secrets across different microservices. And what are the messaging services we can use to implement the PubSub pattern and the event sourcing pattern? We have our Azure Service Bus, which supports queue or topic subscription model. And there's a simplified version of queue on Azure Storage account. And there's also Event Hub and Event Grid. So there are a lot of options. If you want to implement event sourcing pattern, you should have a look on this managed service rather than building the messaging system yourself. So here is a simplified architecture diagram. That's I think it's easy when we build a POC. So as we can see, we have an API gateway here. If the API gateway supports WebSocket, then we don't need this signal. Whereas if our API gateway doesn't support WebSocket, Azure has a great managed service called Signal service that can help us to manage our broadcasting service. So I like to place a VNet to protect our microservices, so the communications within the VNet are guaranteed to be secure and on Azure SLA. And we have our service bus, which we can use as our PubSub pattern. As we can see, each service has its own data store. It can be either Cosmos NoSQL or SQL or Cache or Data Lake, whatever data store. And as a cross-cutting concern, we can use Azure Key Vault to store our keys and secrets. We can use application insight to monitor our applications. We can use managed identities. And we can support different types of front ends, whether it's desktop that you've done with different technology like Electron, or it's a web front end. Now, so we've done enough discussion. Let's get on to a demo. So in my demo, I'd like to show you how I use Ocelot to build an API gateway, and it offloads traffic to subsequent service. We start with adding the Ocelot package and loading the configuration files. Similar to how we load app settings, we can load load the configuration files for different environments. And then we need to do some configuration in our Startup.cs class. We register the service and then we use the service. There's nothing special compared to other libraries. Now, sometimes we want to use Swagger, so it's easier for us to play with our APIs. The way we add Ocelot Swagger is by bringing some additional packages. And we add Swagger for Ocelot, and then we also add the UI. Next, if we want to add some authentication schema, for instance, JWT or cookie schema, we can do so by adding our schema in our API gateway, the same one as where the Ocelot is hosted. And here's an example of an Ocelot.json configuration. As we can see, there's an upstream pattern that we define. So what it does is that whenever it gets some request from an upstream pattern, it will be mapped to a downstream pattern to our downstream service. Apparently, this is at local. I'll show you the configuration file in a bit. But it's going to route the traffic to downstream service. And if there's any authentication schema, we need to register it here by referencing the provider key. And Ocelot support a lot of features. One of the greatest features I like is the header transform. What it means is that it can extract out certain information in your authentication token, for instance, in JWT token. We can extract out the claims and then transform it to the headers to the subsequent service. so that your subsequent service can reference the header directory rather than passing and validating the JWT token again. And if you want to use Swagger to interact with subsequent service, what we have to do is to add this Swagger gen definition in the subsequent services, so that on the Swagger UI we're able to call subsequent services. All right, so next, let's get to the code. So first of all, let me quickly show you the coding structure. So in the demo that I've prepared, we have an infrastructure folder as well as the source code. So I prepared the API gateway and 2 subsequent services. So first of all, let me show you the infrastructure. I have a bunch of bicep files. I'm pretty sure that you know what bicep is from William's awesome talk, which happened on, I think, the other check just now. So I'm not gonna expand too much in explain what bicep is and how things are bolted up, but there's a nice feature I like about bicep is that we have a visualizer on VS Code. And as we can see that we have, let me zoom in a bit. We have multiple services. We have API gateway, we have web service 1, web service 2, which I host them on app service plan. See it here, the Linux app service plan, server farms. And yeah, we can move this to make it easier for us to read. What they do is that they all reference the same app inside, or reference the same keywords, so that we don't need to store the any credentials across different microservices. That's nice and cool. And different service can have its own data store. You don't see that structure that clear here because they reference the keywords and to have access to the database. And I'll also show you how we can place VNet. I don't have VNet in these bicep files because for the sake of simplicity, but I'll show you on Azure portal in a bit. So let's go over to the code. First of all, let's have a quick look on how we scaffold the API gateway. It's nothing different from a normal web API project. As I showed before, get bigger. As I showed before, we can load the Ocelot file and a different environment. If we look at the Ocelot file, which we can run it locally, it has it's a JSON file and it has an object called routes, and another one is the Swagger, which we use to configure Swagger, and also a global configuration. So we can have different upstream patterns mapping to different downstream patterns over different protocol, and certainly different ports. And I wouldn't demo the DevOps process, but in your DevOps process, you need to somehow do some JSON file transformation, or you can generate these production Ocelots yourself. Programmatically. So for instance, on Azure, the services all use port IT, so we need to have port IT here, and then the downstream service can be different URLs or your own DNS, then managed by your DNS provider or Azure DNS zone or DNS global. Now, as we saw before, we have the Swagger key that maps to the Swagger definition for subsequent service. And also the authentication schema that we want this gateway to transform. And also we need to substitute the base URL to be where your API gateway sits. So this is the API gateway, and I've also prepared 2 subsequent services. So we have service 1, which does nothing but just returns some data, showing that it's actually return data from a subsequent service. And I prepared a login endpoint. Usually we want to wrap this to a service, but I just added a controller for the sake of simplicity. We can generate some JWT token, and we want that token to be validated by API gateway rather than subsequent services. As you can see, I haven't added any JWT token schema here apart from the Swagger definition, which help us to use Swagger. The other service that I also prepared is that we can try the header transformation. We expect to see the client that we transformed by API gateway rather than we providing it on the API core. So let me just go back a step. So on service one, what I prepared is, sorry, this one. In the login process, we've added a client called a special client just for testing purpose. And we want to see that these client can be extracted out by our API gateway and attach it to the subsequent call to service B so that service B can recognize it. Okay, so enough talk about the code base. Let's look at the demo in action. So what I have is I have an API gateway, just making sure that I'm on the API gateway. Since we've configured Swagger, well, we can see that from API gateway's perspective, we can see the definition for service A and also service B. So just do a quick test, make sure that it works. So it says hello from service 2 controller. I use A, B, and 1, 2, interchangeably. If we call service 1, then we can see that it says hello. Now, if we are trying to access an endpoint that requires authentication that we defined in our Ocelot file, what we potentially would get is 401 unauthorized. This is the same with the endpoint on service B. Remember that we want to see the header that's been transformed here. So, but for now, we can't access it. We get 401. Okay, let's get back to service A and let's log in. So let's put in some username, just like Patrick. I haven't validated, so it's a proper email, but let me just put in something. All right, something random. Now, it generates a JW token, and let's quickly observe what this JW token look like. JWT. So as we can see, that it contains the name ID and the email. Well, this is not an email. I didn't validate it. Sorry. But what we should highlight on is this special client. We want to see this being passed from the being extracted from the client that passed to API gateway, but also being recognized by subsequent service. All right. So let's go back and grab a copy of it. So the cool thing about Swagger for Ocelot is that you can authorize it here. You only need to authorize it once, and all the subsequent services can leverage it. So the first thing, let's test this endpoint that requires authentication. When we hit execute, remember we used to get 401, but now we get 200. And now let's switch to service B, and here let's try see if we can get a header. So if we click execute, we get the header out. So if we review our code a bit, just make sure that we understand how it works. Service 2 with auth simply just get the header and return this in the 200 response. So now, let's test. If we try to pass it with different header, will it get this header or the header is transformed? If we click execute, we see it's not taking the header that would pass to it, but it transforms from the API gateway. So this way, your API gateway is the actual entry point, and it coordinates the traffic and attach the information you need to attach to subsequent services. This is great. So I've deployed it on Azure. If we jump onto Azure, what we can see is, let me return a step back. We have a bunch of, maybe we need to make it a bit smaller. We have a bunch of services we provisioned on Azure. There's nothing special apart from the VNet configuration. So as I mentioned before, we want to have a VNet to protect our service. So what that means is that we can access the endpoint via API gateway, but not the services themselves. So let me quickly show you what I mean. If we click on one of the microservice and we click on the URL, we can see it because I haven't put the VNet access policy in place. But if we go to another service that I remember, I have put in the access policy already in place, we'll get 403. And the reason why we would get 403 is that we have the networking configuration in place. By that, what I mean is, if we scroll down and move on to the networking session, bear with me, networking, there we go, it's over here. We can see that we have an access restrictions on. So what the access restriction is that it only allows the traffic that's being sent to it within the VNet. And it denied all the other traffic. So how come the API gateway can offload traffic to it? It's because we've configured it to do so by adding the API gateway to the VNet. And that's done in the networking session over here. So as we can see, we have a VNet integration on for the API gateway. So what this means is that the outbound traffic that's being routed from the API gateway is going to go through the backbone network on Azure under this VNet and subnet. So whenever you impose an access policy on the subsequent microservices, only the traffic that you config to allowed will be allowed. All the other traffic from the other public request will be denied. So just as a quick proof, if we take the access policy off from the service that we had the access policy on, what's going to happen? Let's see. I can't find networking again. All right. So here, this one. So if we take this off, remove. So now we don't have any deny policy. So by default, it allows all the traffic. So after that, if we try to access service 1 again, we'll see that we're able to access service 1 from its own URL. So by leveraging VNet, it's easier for us to protect our microservices and offload the security and compliance concern on Azure SLA. So that is great. We can have less concern so that we can have a better productivity on delivering the business value on the main application. Okay, with that, I've demoed how we use Ocelot to build an API gateway and deploy API gateway as app service on Azure. Let's go back to my presentation and see a quick summary. Today, first of all, we've compared Monolith and the microservices on an overview level. And we understood that Monolith is not completely wrong, while microservice has its own challenges. Although I believe that down the track, when the business has become more and more complex in the world, in the modern world, the microservices tend to be the architecture of preference for most big organizations. And we also had a deep dive into different key elements of a microservice and the cloud patterns that we want to advocate when implementing microservice. We also spend a lot of time looking at the services that Azure offers to help us implement those clean architecture and those good cloud patterns. And we've also seen a demo of how I build a quick POC of using Ocelot as an API gateway and the other subsequent services in microservice architecture. So with all that, that's the end of my presentation. There are references. I have uploaded the code that I showed you to my personal GitHub account. I'll be keep updating it to add more stuff to it. So hopefully we can use it as a good template to start with microservice architecture. And I also reference to this Microservice.io as a great resource for different cloud patterns. All right, with all that, thank you very much. Still have 5 minutes to go, so if there are any questions, you're welcome to drop them, or if you want to discuss offline, my maybe let me just rewind to this slide. You're welcome to post them on the social media links